Hello and welcome once again for another ES340 video. This is Day 16 Example Problem 2. 3 pounds of carbon monoxide, initially at 180 degrees Fahrenheit and 40 pound-force per inch squared, which is the pressure of course, undergo two processes in series. Process 1 to 2, which is constant pressure, to a temperature 2 of negative 10 degrees Fahrenheit, and then process 2 to 3, which is isothermal, and goes to a pressure 3 of 10 pound-force per inch squared. Then we're going to let T0, this is the environment, right? T0 be 77 degrees Fahrenheit, and P0 be 14.7 pound-force per inch squared. And we're going to ignore motional and gravitational effects, which should immediately tell you kinetic energy and potential energy can be ignored. Okay, so assuming the ideal gas model, A, represent each process on a PV diagram and indicate the dead state, and B, determine the change in exergy for each process in BTU. Okay, so let's first start with the PV diagram. Which should be obviously familiar at this point. And we start off, in a temperature. Let's call this state 1. I'll just mark it off up here. And the temperature T1 is 180 degrees Fahrenheit, which, by the way, is the same as approximately 640 degrees ranking. It's about 460 degree. You basically add 460 essentially to the Fahrenheit to get it to ranking, which will be important in a moment. And the pressure, of course, P1 is equal to 40 pound-force per inch squared. And then it goes to a process 2 with a lower temperature, which indicates also that there'll be a lower specific volume, but the pressure remains the same, right? So we're going to go in this direction, 1 to 2, and at that place we have a temperature T2, which is something we're going to have to find. Oh, right, we were given the T2. T2 was minus 10. There we go. So that's going to be minus 10 degrees Fahrenheit, which is the same as 450 degrees ranking. And the pressure there obviously has to be 40 pound-force per inch squared. And then I kind of ran into this a little bit, but maybe we'll go from 2 to 3 being blue. It's going to be at a constant temperature, isothermal, right? It was isothermal for process 2 to 3. So the isotherms kind of look like this on the PV diagram. And it's going to come down to state 3. And state 3, we were given that the pressure is 10 pound-force per inch squared. But the temperature obviously is the same. So T3 has to be equal to 450 degrees ranking because it was isothermal. Okay, going from 2 to 3. Okay, so we can actually obviously map all of these things out, and we know for part B we're going to be interested in the dead states because we want to find the change in exergy, right? So this is part A. I finished this part. But part B, for part B, we're going to take note of the fact that T0 is equal to 77 degrees Fahrenheit which is about 563 degrees ranking. Uh, 67. I don't know why I got 3 in my head there. So about sorry, my mental math is not doing well today. 537, there we go. That was where the 3 came from in my head. So this is what our temperature is, and our environmental temperature, right? Remember, for the exergy, we kind of have to have environmental values in order to figure out what the exergy is. So we have to compare it to the environment. And this is equal to 14.7 pound force per inch squared. Okay. So now, because we know these values, I'm going to also note that at least the specific exergy. So we wanted to figure out what the exergy difference was. But it's going to be much easier to work with specific values, because that's where we're going to get off the tables and then just work backwards. So we know that say 2 minus E1, that's going to be the first change, because we have two processes that are happening. E2 minus E1, well, that's going to be equal to M times U, in this case of T2, let's just call it 2, minus U1 plus P naught times V2 minus V1, right? That's going to be part of it, minus, plus, I did say plus, sorry, minus T naught times S2 minus S1. And since the kinetic energy and potential energy terms that we had here are going to be ignored, I'm not going to write them, but just remember that we would have had them here. This should be times M though, right? I forgot my M's here. Times M and T naught times M. Okay, so that's going to be my change for that one. And then obviously E3 minus E2, it's going to be a similar thing. It's going to be M times U3 minus U2 plus P naught times M times V3 minus V2 minus T naught times M times S3 minus S2. Okay, so what we're going to then need to do is, let's start with the E2 minus E1 thing that we have. We obviously are going to want the specific volumes, which is easy enough to get. We know what the M is, by the way. We were given that M was 3 pounds of carbon monoxide. So M is equal to 3 pounds. And we're going to just need to get these values, and the U's we can get off of the table. And this it's an ideal gas, right? So we're going to have to do a little bit of work to find that. So first, let's write the difference, S2 minus S1. Well, remember that this is going to be something like S circle of T2 minus S circle of T1, right? So the S values that we find there minus R times the natural log of P2 over P1. Or it could be plus R times the natural log of V2 over V1, whichever one we decided to use. I'm just going to stick with this one. But we are going to need to find V2 and V1. So V1, well, this is an ideal gas. So let's start with the fact that it's an ideal gas, and then we can see why what I'm saying is true. So PV equal to RT, since it's an ideal gas, which means that V is equal to RT over P. So that means V1 is going to be RT1 over P1. And V2 is going to be RT2 over P2. Now, since these are English units, things are a little bit annoying, admittedly. The probably in some ways the most convenient term to use for R. Remember, R is equal to R bar over M, over capital M, where this is the molecular mass. And this comes from table, in this case, A1E. We can find it on A1E. This R bar value, we can read it from section in the book, section 3.11. And I think it's table A1 if I remember correctly. I didn't write that down, but I'm pretty sure, or table, maybe, I don't know. I don't remember the name of the table, but it's in section 3.11. You can find R bar. So R bar, there's two R bars that are given in English units. You might think that going to BTUs is most convenient. If you wanted to do that one, you could. I think in this particular case, it's going to be most convenient to go to the foot times pound force thing and work from there. You'll see why in a moment, but I think that might be the most convenient way. So R bar is going to be equal to about 1545 foot times pound force per pound times degree ranking. Okay, and the thing that we were dealing with is carbon monoxide. So since it's carbon monoxide, you can go and read. What we're going to find is my capital M, again from table A1E, my capital M is going to be 28.01 is going to be the value. Okay, so then what I can do is I can divide this out. So R, hold on one second. I apologize. I'm having a rough day with things here. The units of R bar are actually foot times pound force per pound mole times degree R. Okay. And the units of this, going to the tables, the units of capital M are pound per pound mole. And then when I divide through, I get the units that I originally wrote. I was wondering what was going on there. So that was my fault. I wrote that down incorrectly. So this is foot times pound force over pound mole times degree R divided by 28.01 pound per pound mole. And that'll give me something like 1545 over 28.01, and the units then will be foot times pound force per pound, which is what I originally had written there, degree R. There we go. So that's going to be my R value, and you can obviously compute that out as you wish. So that's my R value, and that's what I'm going to use here. So this is my, say, R of CO, right, carbon monoxide. And what I'm going to do then is obviously substitute that in with the values. So it's going to be V1 is equal to 1545 over 28.01 foot times pound force per pound times degree R. And then the temperature that we had was 640 degrees R, ranking. And the units that we had here for this, now notice that the units of this are in feet. So the pressure, which was given, P1 was 40 pound force per inch squared. But notice that 1 inch squared is the same as, 1 foot squared is the same as 144 inches squared. So that means that I will have to multiply or divide, in this case, by 144. So it's going to be 40 pound force and then I'm going to, per inch squared, I'm going to have to put times per 1 foot squared, 144 inches squared per 1 foot squared, right? So that's what I'm going to have to multiply by in order to get the units into per feet squared, because eventually we want all this stuff to cancel out and get us into feet cubed per pound, which is exactly what this will be. So this works out to be about 6.13 feet cubed per pound. V2, it's going to be a similar process, right? Just using the fact that it's an ideal gas. So that's going to be 1545 over 28.01 times foot times pound force per pound times degree ranking. The temperature was 450 degrees ranking. And I'm going to divide through, again, it was a constant pressure, so 60 pound force per inch squared times 144 inch squared per foot squared, which is going to give me 4.31 approximately feet cubed per pound. Okay, so those are my V1, V2. May as well get V3 as well, right? Why not? While we're working at it, let's go ahead and give V3, which is again 1545 over 28.01 feet times pound force per pound times degree ranking. You can see why this is convenient to do it this way first, because getting the V in terms of BTU would be kind of weird, right? It makes sense to have it in feet cubed per pound, which is why I chose to go this direction. And the temperature stayed constant in that case, if you remember, going from 2 to 3. So it's the same temperature, but now it's a new pressure, which is 10 pound force per inch squared times 144 inch squared per foot squared, which gives me 17.24 feet cubed per pound. Okay. So now we have V1, V2, V3, and we have most everything else, but we're going to need S of T1, S circle of T1, S circle of T2, S circle of T3, excuse me, for the remainder. And then obviously U of, U of at temperature T1, U temperature T2, so U1, U2, U3 as well. So to find those, of course, then we can go to the tables. So table A23E, since we're in English units, and we can find these. So basically now the problem that we're gonna run into is that we're given these in terms of bar. So U1 actually is given with a bar over it off of the table, which is kind of annoying, but it's simple enough to correct for that by dividing by M, by capital M. So U1 bar is going to be equal to 3175.9. This is reading off the table. And using interpolation. I didn't mark off which ones needed interpolation. That was my fault. But either reading off the table or interpolating, we get 3175.9 BTU per pound mole. That's what the value that's read off the table. So that means the U1 is going to be equal to U1 bar over capital M. So that's going to be 3175.9 BTU per pound mole divided by 28.01 pound per pound mole. And similarly, U2 is going to have a bar over U3, so I'll just write U2 is going to be equal to, well, this one, if you read it off the table or interpolate, whatever the case may be, ends up being 2230.85 BTU per pound mole. And then it's going to be divided by 28.01 pound per pound mole. And U3 similarly is going to be is going to be 2230.85 BTU per pound mole divided by 28.01 pound per pound mole. And you might say, why is that the same? Well, they have the same temperature, right? And so the ideal gas ones are only judged by the temperature. So if they have the same temperature, they're going to have the same values there for reading those things off of the table. And then finally, the S circle, and again, those are given as S circle bar values of T1, for instance, in this case. And so that is going to be given as for the first temperature, 48.494 BTU per pound mole times degree R. And obviously then we don't want the bar quantity, we want it without the bar. I know it's annoying that we have to do this, but is it going to be equal to S naught of T1, yeah. S circle of T1 over capital M, so that's going to be equal to 48.494 BTU per pound mole times degree ranking divided by 28.01 pound per pound mole. Similarly, S circle of T2, that one is going to be 40. Let me just make sure I'm reading the right value here. 46.04 BTU per pound mole times degree R. divided by, again, 28.01 pound per pound mole. And that's going to be equal to S circle of T3, because T3 is equal to T2, right? So again, we'll get the same values there. Okay, very good. Now, the final thing is now that we have all of these values, basically just pulling everything together, which is easy enough, right? So E2 minus E1 is going to be equal to M, which is 3 pounds, times, let's write this, let's pull the 3 pounds out of everything, because that's, notice that that M was multiplying everything in this equation up here, right? We had an M here, an M here, and an M here. So I can pull the M out. Let's pull the M out and just and keep all of the rest of the terms. So this is 2230 this is the U1, U2 I mean, minus 3175.9 BTU per pound mole, divided by 28.01, because that was dividing this. This term also was dividing every term, so I can just kind of divide through all of them by that. Pound per pound mole. Then the next term was the P naught pressure. So it's going to be plus P naught, which was 14.7 pound force per inch squared, times, again, that 144 inches squared per foot squared that we had before. And then we're going to want to also convert, so this gets me into pound force per foot squared, but we're now also going to want to convert in terms of BTUs. So this is going to be times 1 BTU, so 1 BTU, I'll write it up here, is equal to 778, approximately, it's not exactly, foot times pound force. So we're going to multiply that by times 1 divided by 778 foot times pound force. So that'll obviously get rid of the pound force. We'll get everything out in terms of BTUs now. That's going to, because we have to obviously multiply time, well, notice that the units here, I should have mentioned this part, the units here give me BTU, and it's going to be per foot cubed, right, once everything cancels out, and we're going to per foot cubed, the pound force goes away, the inches go away, so per foot cubed, and this is going to be in terms of foot cubed per pound, the volume here. There we go. Which obviously will end up getting me BTUs per pound, and then when I multiply by the pounds, I'll get it in BTU, so very good. Then the last term, which is 537 degree Rankine. Remember, the temperatures have to be absolute temperatures, which is why we had to do that conversion, times 46.04 minus 48.494. These were the S circle values, right? Times That's the units are BTU per pound mole times degree ranking. And that's divided by 28.01 pound per pound mole. And you might be saying, hey, wait a minute, why are the S circle values the only thing in here, right? Because I said S2 minus S1, that's got to be equal to S circle of T2 minus S circle of T1 minus R times the natural log of P2 over P1. But remember that for this part of the problem, the pressure remained constant, right? Constant pressure. So because of that, P2 is equal to P1, which means P2 over P1 is 1, and the natural log of 1 is 0. So this term actually just drops out completely from the S2 minus S1 when the pressure is constant. Convenient. So that's why I have that. So that means that my E2 minus E1, when you calculate everything out, calculate out all of those values, ends up being about 25.1 BTU. Now we can do a similar thing. E3 minus E2, well, that's going to, of course, I'd pull out the mass again, 3 pounds, times, well, remember that we said U3 and U2 are equal to each other? So that means that U3 minus U2 is equal to 0. Okay, so I don't need to include that term. That term obviously is going to fall out. So that means that I get 14.7, that's the P naught times V3 in this case minus V1. So 14.7 pound force per inch squared times, again, the 144 inch squared per foot squared times the 1 BTU per 778 foot times pound force. Boy, and I'm going to run out of room here, times 17.24 minus 4.31 foot cubed per pound. Phew! So that's that term. Minus the T naught, which is 537 degrees ranking, times minus 1986, excuse me, BTU per pound degree ranking divided by 28.01. And then times the natural log of 10 divided by 40. Now this is my R value. And the minus sign was just, remember, it was minus R times the natural log of P2 over P1. So that's where the minus sign came from there. This is what and obviously as long as the pressures are in the same units, I'm safe here. I can just ignore the units. And they should be unitless inside of the natural log. So what that leads me to is E3 minus E2 is equal to minus 52.8 BTU. So what we can conclude here is that we moved further from, when we went from process 1 to 2, we moved further from the dead state. And when we went from process 2 to 3, we actually got closer to the dead state, right? Which is obviously something that's possible. Okay, so that's all that I have for this video. Hope to see you again soon.